Good afternoon.
Good afternoon.
I would like to introduce two great speakers for this workshop, Nina Zumel and John Mao. So I wanted to introduce Nina. Nina started her advanced education in electrical engineering at UC Berkeley and holds PhD in robotics from Carnegie Mellon. She has worked as a scientist at SRI International as chief scientist of a price optimization company and founded a contract research company. Nina is a co-founder and principal consultant at WinVector, together with John. A San Francisco data science consultancy. Nina is the first author of Practical Data Science with R. She blogs about technical issues on her blog as well, and writes about myths. And you have another blog. I'm not going to read the whole URL here. Now, John is a principal consultant and also a co-founder at WinVector. The company has been founded 8 years ago, San Francisco. John has a PhD in computer science from Carnegie Mellon. Is that where you guys met? No? Oh, that's right. But you went to Carnegie Mellon for a PhD too?
Yes.
That's right, all right. And has worked on biotech research, program trading, and run research groups at Shopping.com, which is an eBay company. John is also one of the authors of Practical Data Science together with Nina. He also writes the blog for WinVector and is a Rotary member actively serving his community. Yeah, anything else? All right, thank you.
All right, everybody hear me? Well, thank you everybody for showing up. I'm kind of gratified to see that the room is completely full, maybe even overfull. We're going to split this workshop into two parts. I'm going to give the first part, and John is going to give the second part. The first part of this workshop is I'm going to be talking about sort of the operational aspects of data preparation, basically data cleaning and the basic problems that you can find in data and how to deal with them in R. And we're going to give some examples of the common issues and also how to address them. And then we're going to give some examples of how to automate the data treatment that I talked about, including one very concrete example, which is the B-tree package, which is a package that we've developed for automated data cleaning. And then I will turn it over to John, and he's going to talk about some more statistical things that have to do with data cleaning. Now, throughout this workshop, we're going to talk about...
Pardon. Sorry, we're having a little technical problem. Just take a second. Can we go to do this stuff? Let's see. What was that? Yeah.
So this is basically the workshop where we show you what you do and we give you all the sources.
Yeah, that's better.
To take away with you so you can run again later. So there's no requirements to work along. You good?
Yeah, thank you.
Continue?
Yes.
Okay. So as I was saying, through this workshop, we're going to keep a goal in mind that the data cleaning that we're going to do is with the goal of using machine learning to build a predictive model. And while this might sound kind of obvious, I want to call it out to you explicitly, because we're going to use this goal to evaluate the different types of approaches that you can take to data cleaning. What you want to answer is the question is, if I treat this data in a certain way, does that help or does that hinder the machine learning process? And the answer is going to depend on the nature of the data, and it's going to depend on the nature of your problem. So what I'm going to do is I'm going to run through a bunch of different approaches, and try to give some, pluses and minuses of all of them, and then discuss the ones that we picked for our particular needs, just because that's concrete. And they might be the same choices that you make, and they might not. So let's talk about data preparation. So one of the other things that I want to emphasize about data cleaning, or automated data treatment, is that it's really not a substitute for getting your hands in the data. It's always really important that you look at the data, that you explore it yourself, and really get to know it. The reason that you want to automate it is that there are going to be some issues that show up again and again and again. And if you can automate those issues, then you have more time to deal with the more domain-specific aspects of your data. So what we're going to talk about are some of the typical data problems that can be automated. So here's a kind of a list. We can deal with bad numerical values, that is missing values or not numbers, or sentinel values, that is values that appear to be numerical but are really symbolic. So seeing -1s or all 9s often mean they're not really literally numbers, but they're actually code for not applicable or not a number, or data out of range, or what have you, and you want to be able to identify them and fix them. For categorical variables, you want to be able to deal with missing values and also novel levels. You may have levels that show up in, that do not show up in your training data that you see later when you try to apply your model, and this can often cause issues, especially in R. So we want to discuss some of the ways that you can handle those. Another big problem is, for many applications, is categorical variables with too many levels. This is a problem for a lot of machine learning algorithms because all of the levels of a categorical variable are essentially, under the covers, variables that go to machine learning. So if you have a whole lot of levels to your categorical variable, then you really have a lot more variables than you think you actually have, and you have to be able to deal with that. And finally, there are invalid values, values that are out of range, or categorical levels that just don't make sense. And we're not really going to talk so much about this last aspect because that's really more domain specific, but we're going to talk about the stuff that comes before that because these are things that show up over and over again and that you want to be able to deal with. So the first example, let's talk about bad and missing numeric values. So let's just suppose that we were trying to build an application to predict the price of the sale price of used cars. And one of the variables that we wanted to use was miles per gallon. And it could very well be that under the covers that this value came from a calculation that you had no access to. And also there's all the issue that, especially these days, not all cars mileage is a meaningful variable. For example, with electric cars, what does mileage mean for an electrical car? So you could get bad numerical values in that column. For example, you could just get for an electric car, you could just get an NA for not applicable, or you could get an infinite if somebody did a blind calculation divided by 0 without meaning to. Or you could just get bad calculations that give you not a number. And you want to be able to deal with those numbers, those bad values, in a reproducible and automatable way. So how do you deal with them? Well, before we talk about how you deal with them, let's talk about where bad values actually come from. There are basically two kinds of bad values in numerical variables. You can have missing variables that come from what I call a faulty sensor situation. That is, values that are simply missing at random. So for example, that could just be because whatever's taking the measurement just failed for no reason, or just one day people failed to collect the data. And it's got nothing, it's just random. And with a faulty sensor situation, what you usually tend to assume is that data that is missing has the same distribution as the other values, it just happened not to get collected. In that situation, then you can actually infer what that value might be by looking at what you have actually observed. So the mean of the value might actually be a reasonable stand-in. The other problem, the problem that's actually going to be more common in the situations that we see, are what we call systematically missing variables. And the electric car example that I just gave is a good example. Electric cars don't really have a meaningful notion of mileage in the same way that hybrid and internal combustion cars do. They do behave differently electric cars do behave differently from gas or hybrid cars. So to substitute in the average value of all of the gas or hybrid cars for your electric cars as a mileage is not really meaningful, and you don't want to do that. So you keep in mind those two different kinds of bad values. So what do you do then? Well, there are a number of different possible ways that you can deal with these missing values. The easy way, the naive way, is simply to skip rows that have missing values in them. And under the covers, this is what R actually does. And if there are not very many missing values, this is actually not such a bad idea. I mean, it's certainly easy, and it may not hurt you very much. The problem comes when there are when you have a lot of columns, and all of these columns have maybe a few missing values in them, and then if you start looking, you take the union of all of the rows that have something missing somewhere, those numbers start to become very large. And so just skipping those data rows is not a good idea. So then you want to look at other approaches. One thing you can do is you can try to build several models that get around the columns that have incomplete data. So basically, if you know that sometimes mileage is not going to be there, you can have an alternative model that you can fall back to that you can use when you see that the mileage, for example, is missing. This is sort of a hierarchical approach. So as much data as you have, you can use those. Otherwise, you back off. One of the more popular methods with statisticians is variability mutation. There's actually a big literature on this. And that is you build models using your other inputs to guess the values for the missing variables. So for example, the very, very simplest thing is just to use the average value of what you have actually observed as the filling. And that's great if you have a faulty sensor situation. But that's not going to be so good with situations where the data is missing systematically for the reasons I just talked about. So you might want to go to something more pragmatic. For example, one of the things you can do is just replace all the missing values with a harmless stand-in, say 0, or the average value, and then add additional notation, say an additional variable that records when you actually did the substitution. So basically, you're keeping extra information about the data cleaning that you did. And this is actually really useful in many data science situations because generally we're in a situation where missing values are in fact systematic, but that is data that comes from a different population. And it's informative usually for what you want to predict. So sometimes it can be one of the more informative signals to record exactly when certain data was missing. So we'll take, for example, one pragmatic solution of how to deal with missing numerical values. So we have, on the left, we have our original data row, miles per gallon, with its bad values in it. And what we've done is we've transformed it into 2 rows. One where we've substituted in the average observed value for the bad variables, and then added another column, which we're calling here MPG is bad, which is true whenever we make the substitution. And the idea is that we're kind of hedging our bets between systematic and faulty sensor situations. If in fact this really is a faulty sensor situation, then all the information you need is in the first variable, MPG. And a good machine learning algorithm should know that it doesn't need the other column, and so it will deal with it appropriately. On the other hand, if you have a missing systematic situation, then what we've done is we've given the machine learning algorithm an additional degree of freedom so that it can sort of correct any mistakes that it might make because it has sort of spurious values that we've substituted in. So that's the kind of thing that we can do. The second example that we have is dealing with unexpected or novel categorical levels. So this is kind of the categorical analogy of what happens with numerical variables. So for this example, suppose that one of the input values we have is state of residence of our customers. And in our training data, so let's say that in our training data, we have mostly customers that come from the West Coast or near the West Coast. So most of them come from California, Nevada, Washington. Sometimes we don't know where they come from, so there's going to be an NA. But for the most part, this is what we've observed. Now what happens if later, after we've built a model, we want to apply it to a new data set, and within this new data set, we have people who come from states that we didn't see in training. For example, here, in this, in the new data that I have on the right, we have a customer that comes from Wyoming. What happens? Well, what will happen if you try to run an existing model that was trained on that training data on this new data, it's going to fail because it's going to see this new level Wyoming, and it's just going to say, I've never seen it before, can't run, and it will crash. So what we're going to try to do is find a solution that keeps us from crashing and hopefully also gives us a really good answer, a good prediction for the Wyoming customers as well. So on the way to the solution, let's sort of step back and look at how categorical variables are implemented under the covers in R and actually most machine learning systems. A categorical variable is generally shorthand for a set of several variables, one for every possible level of the category. That's 0 or 1. It's 1 when that category is that value, and 0 otherwise. So for this particular example, when we've got 5 states, including NA, that would really be expanded to something like 5 columns, each of which is 0, 1, and it'll be 1 for the appropriate state and 0 otherwise. And this is sort of important to know because this is how we're going to deal with, this is how we're going to represent the way to deal with missing variables and novel levels. So let's look at 3 possible solutions for dealing with those missing variables. So in addition to having the states that we know were in the training data, let's say that we also know what the training data proportions are, and that's up in the top right level, top right corner right there. How do we deal with new levels? There are 3 ways to represent a new level, given the training data that we previously had. We can represent a novel level as being all the levels that we've observed proportional to the known levels. So basically, given that we know what the values are, instead of having 0, 1 in those columns, we're just going to have a fraction that represents the training data proportions. And this is kind of the analogy to putting in the mean value in the numerical variable. So we don't know which level this is, so we're going to assume that it's all of them. And it's also kind of analogous to assuming that the novel level is actually a transcription error. So it's something that we have seen, we just don't know which. The other thing we can do is we can treat it as no level, which is it's kind of obvious. Well, we've never seen it before, it's nothing we've seen, so we're just going to represent it as all zeros. And the third thing we can do is we can say a level that we've seen for the first time behaves like rare levels that we've seen before. So basically what we can do is that when we have our training data, we can pool all the rare levels into one level called rare. Usually, in many situations, when you have a number of different categories, many of these categories, some of these categories are going to be more popular than others. You have a question?
Yeah, just quickly, referring to the mean, do you ever consider using other measures of central tendency that are more robust to outliers? Median, for example?
You can. Yeah, I'm using mean as an example.
Okay.
Mean or median, all of these things, I mean, they all essentially have the same underlying assumption. Basically, that what is missing or what is novel is in fact something you've seen before, you just don't know which one it is.
The thing is, if you have a bimodal distribution, for example, the
Right.
mean can actually not occur ever.
Right, right. So yeah, so basically, yes. So you can do that, but we're not talking about that right now. So if you have a novel level, and if you have levels that some levels are common and some levels are rare, you can pool all the rare levels into one level called rare. And then every time you see novel level in future applications, you can say, well, a level that I'm seeing for the first time is sort of like a level that it was so rare that it didn't show up in the training data, but maybe it behaves the same as those other rare levels. And so I'm just going to code it as rare. And another way of saying that is that we're going to treat the uncertainty as being proportional to all of the rare levels. So here in this example, NA and Nevada were both more rare or less frequent than the other states. So to treat Wyoming as a rare level, we would sort of, it's kind of like splitting the difference between saying it's NA or saying it's Nevada. Okay, so the v-treat solution which is the V-tree solution is sort of a variation of that last one. Basically, what we do is we take levels that appear fewer than n times, where n is chosen as a definition of rare, and we pool them to a single level called rare. So in this example, suppose that our training data had some 4 very common states, and then 3 states that were, very unusual compared to the first 4. Then we take Wyoming, Idaho, and Colorado here, and we pool that into a single level called rare, and then just treat it like a level and work with it as if it had existed before. Then we evaluate all of the levels for their statistical significance, and John will talk a little bit more about how we do that. Levels that don't achieve statistical significance, we just code as no level. So basically, going back to this case, we would be treating it as approach 2. We're just going to say it has no value. It's all 0. And then novel levels that we see, we would code to rare if that variable made it through the ZAP phase. Otherwise, we're going to code it to ZAP. And then the third example that we have is categorical variables with many levels. And this is sort of an extension of the first, of the situation that I just talked about before. We can have a category called like zip code. There's something like 40,000 zip codes in the United States. So potentially, if zip is one of your categorical variables, that's a pretty big one. Of course, you're probably not ever going to see them all, but you might see a lot of them. Now, if you have too many levels, that is a computational problem for a lot of machine learning algorithms, because as I said, all of the levels will be expanded to that many. If you have k levels, that will be expanded to k indicator variables. And a lot of machine learning algorithms cannot handle very, very, very wide data sets, not very well at least. So that's a problem. And the other problem, of course, is that you will inevitably have an alpha level problem, because if there are that many levels and your training sets are not big enough, then you're bound to run into values that you've not seen before. Well, the best thing to do with this is to remember that often that when you have something like zip code or business code or some other categorical variable that has a lot of possible values, that usually this is a standard for some additional information. For example, zip code is often standing for demographics about the people who live in that region. The average price of their house, or their average income, or the size of their family, or whatever. And so, when possible, the best thing to do with categorical variables like that is to use them as a join key into domain knowledge. So, for example, if we have a problem where we're trying to predict the sale price of houses on the market, and one of the variables we have is zip code, what we'd really like to do is use that zip code to look up, maybe from an external data source, what the median home price or the average home price is in that zip code, and use that value of average home price in your model instead of the zip code. And that's the best thing to do, but it isn't always possible in all situations. So what I'm going to talk about are things that you can do when you can't actually use the categorical variable as a join code. So if you can't actually look up the information you really want from an external source, then the next best thing you can do is try to derive it from your data. And this is something that we call impact or effects coding. So essentially, if you're trying to predict home prices, and one of your input variables is zip code, then from the data that you already have, you can see what the average price of a home is, mean or median, whichever average you'd like to use, for the different zip codes. And you can also see what the average price is for your entire data set. And then what we call the impact code is to represent what the impact of all of those zip code values is on the average price. So basically, if the global average price in your data set was $639,000, then given the other information that you've gotten from your training data, you can see that houses from the 90011 zip code might be, on average, $250,000 less. And houses from the 94127 might be, on average, $300,000 more. And so what we've basically done is we've encoded the impact. So this is kind of like taking the data that we would have ideally gotten from external data and deriving it from the data set that you have. The other thing to notice about this is that this is actually what we call a Y-aware encoding. Basically, what we're trying to predict, the outcome that we're trying to predict in this case is average home price, and we're using that directly to do the impact coding. The impact coding is in some sense a one-dimensional model that takes this categorical variable as an input and predicts what you're trying to predict. So you're going to have different coding depending on what it is that you're trying to predict. So here's just an example of using the impact code that we learned in the previous slide and applying it to a bunch of different zip codes. So we transformed the zip code into a variable, into a value that we're going to use in our model, zip impact. And we can also deal with novel zip codes that we've not seen before by simply coding them to 0. And this is the equivalent of assuming that their average home price in that zip code is the same as the global average that we observe, because we have no other information besides that. So I'm going to take a slight sidebar here, and I'm going to talk about something that's also kind of important. The thing about indicator variables and the thing about impact coding, what they both have in common, is that they're ways of taking non-numerical variables and converting them into numerical variables. And the numerical variables is what the machine learning algorithm wants to work with. Now, the nice thing about R is that it does a lot of this under the covers for you. It'll automatically turn the categorical variables into the appropriate numerical representation before applying machine learning algorithms. Not all systems do that. For example, scikit-learn only takes numerical variables, and it doesn't do any of those translations for you automatically. Scikit-learn algorithms don't. But it does provide a function called one-hot encoder that can do the conversion of categorical variables to indicator variables by hand. You just have to remember to do that explicitly. Now, something that people are often tempted to do, rather than go through the one-hot encoding, is they'll try to hash a categorical variable instead. So basically, the simplest case is you just take all the possible categories that you have, the possible levels that you have in your category, and you just code them. So this is category 0, category 1, category 2, category 3, and you put that numerical coding into your machine learning algorithm. The problem with this is that it loses some of the structure of the original problem. And also, it puts in some structure that wasn't really there. Basically, it's going to imply similarities and nearness between different categories that might not have been there in the first place. So for example, if you were trying to code colors, red, blue, green, and you hash that to 1, 2, 3, it's going to make the colors, red and blue look like they're closer to each other than red and green are, even though they're really not. I mean, that's not meaningful, because that's what the numbers are going to look like. And if you're using a machine learning technique that relies on similarity or distance, so for example, you're trying to use a linear technique like linear regression or generalized linear regression or logistic regression, or you're using a machine learning technique that depends on distance, so for example, nearest neighbor or SVM with radial basis functions, you're going to get misleading results if you hash. So you really want to do either an indicator variable conversion or an impact coding. Or you want to use a machine learning algorithm that can actually undo the false structure that you put in. So for example, a tree-based machine learning algorithm like random forest or gradient boosting can sort of undo a hashing and return the structure that was really in the problem. So kind of the short mantra here is that you want to impact code rather than hash, but if you are going to hash, then you should use something like random forest. Okay, so those are the kinds of the problems that are easy to automate. And I'm going to talk about a specific example of a package that will do some of this automated variable treatment for you. Now, this isn't necessarily the solution that's going to be the one-size-fits-all for everybody in this room. It's something that we developed because it reflected the kind of problems that we've observed with the data that we work with and the people that we work with. And so it's kind of tuned in that direction. But I'm giving it to you as a concrete example of an automated system, and that hopefully, that even if you don't find it directly useful, you can go to it for inspiration for the kinds of things that you might want to do to automate data treatment of your own. So with vTreat, we have kind of a two-step process. We use the training data to design what we call a treatment plan. It collects all the statistics and all of the important values that we need from the training data in order to do the kind of data treatments that we saw previously in this talk. And then we take that treatment plan and we apply it to the data sets to transform them into a form that can be used in machine learning algorithms to learn the model, and also the same form that is used to apply the model to the data. And in the slide deck, which hopefully you all will be able to download if you've not downloaded it already, I have examples of the user interface, but I think at this point, it'd be better just to kind of show you what it looks like, sort of more or less live. Okay, so if you actually have downloaded the material that we gave you, there is a folder called Basic Treatment, and there is a markdown file called vTreat Garden Path. So I'm just going to show you a really, really simple example of applying vTreat and kind of walk through it. If you have this, you can kind of walk through it along with me. You can run it if you want, and if you don't want to, well, then you can just sort of either watch me or look at the output of it, which is also now. So, I'm just going to load the libraries and load the data. And for this example, I'm going to use synthetic data because it just makes what I'm talking about easier to show. Okay, so let me just show you what the data kind of looks like. So we're going to try to predict a numerical outcome, y, and we're going to try to predict it based on 3 variables. One numerical variable, x1, which is going to have some missing values in it. 2 categorical variables, one x2, which is going to be sort of a small categorical. It's got 5 possible values, I think. Yeah, 5 possible values, 3 of which are very common and 2 of which are sort of less common. And then last variable is x3, which is also a categorical variable. It's going to have 200 possible values, so it's kind of a large categorical, all of which are equally likely to show up. And the way I've designed the synthetic problem is that y actually does in reality depend on all 3 variables and on all of the levels of these variables. And so I just want to show you what happens. So here's the, I'm going to show you here. This is kind of how we define the treatment plan based on this data. What I'm going to do is, actually, let me show you this. I made several data sets. We're going to assume that we have a training set of 1,000 rows, and we're going to have a test set of 1,000 rows to evaluate the model. And we're also going to use, rather than using the training set to prepare the data, we're going to have an additional set that we call calibration set. This is kind of best practices of 500 rows that we're going to use to create the treatment plan. So the treatment plan takes as input the set that you're going to run it on, that is the calibration set, a list of the variables that you want treated, and what the outcome variable is. So if you just run those. And I think, yeah. Oops. The treatment plan actually has a bunch of different structures in it, but the one that's actually the most important to look at is what we call the score frame, which sort of summarizes a bunch of things about the treatment plan that we've just created. Okay, so what we've got here in the treatment plan is we've got a list of what the treated variables look like and what they're called. and what the original variable they came from, which original variable they came from. So we had 3 original variables, x1, x2, x3. And what happens is the numerical variable x1 is transformed into 2 variables, x1 clean, which is basically another numerical variable with all missing values and bad values treated. And then x1 is bad, which is the additional column that we create to mark when we've done substitutions for bad values. Then we've got, for the small categorical x2, we've got 3 indicator variables for blue, green, and red. So those are the 3 common levels in x2. And then we've also got impact-coded variable that represents all of them as one variable, rather than an indicator as the one variable model. And then for x3, which was the large categorical, we've got, again, the impact-coded variable. And we've got one indicator variable, which was called rare, which is basically a pooling of many of the rare variables that we saw. Now, one of the things I want to show you is that the last column here of this score frame is actually the significance of all of the variables that we've estimated after we run treatment plan. And one of the things that I want to point out is that the x3 variable looks like it's not significant. It's got a very large significance value. And what I said earlier is that we know that actually x3 is significant by design of the synthetic data set. So kind of want to talk about what happened here. And what happens here is that this was, as I said, this was a very, x3 was a variable that had a lot of possible levels in it. 200 of them, in fact. But the calibration set that we were using only had 500 rows in it. So basically what happens is that, on average, every one of these levels only showed up maybe 2.5 times. That means that's on average. That means that some of them only showed up once or twice, or maybe not at all, and some of them maybe showed up 4 or 5 times. And that's really not enough information for a machine learning. That's not enough information to sort of measure the effect of all of these levels on the data. And so what the significance scoring has determined is that there's just not enough data, so I can't call this significant. So one of the things you can do when you see something like that, if you know that it should be significant, is that you might want to use like a larger calibration set. So if we tried the same thing with a calibration set that was 2,000 rows instead of 500. And run the score frame again. Here you see that it's got a more realistic, more optimistic, I should say, estimate of the significance of the calibration set, of the x3 variable. So we have a treatment plan, and now you want to apply it to the data to treat the data before you put it into the machine learning algorithm. So in order to do that, we have a call called prepare. And what prepare takes as an input is the treatment plan, the data to be treated, a significance pruning factor. So basically, since we have a significance estimate on all of the variables that we've seen, we might want to prune the ones that look like they're insignificant. And we're going to do that. We're going to prune the ones that are significant to, that are not significant to the 0.5 level. If you want to turn off pruning completely, you can do that by sending prune sig to null. And then do color equals false means that we are not coloring all of the data that we observed to be within bounds of the training data that we saw before. So we can treat the training data, we can also treat the test data. And then we can see kind of an idea of what the data looks like. And we can see that it's all numerical data, and it's all clean, there are no missing values or anything. So then, now that you've got sort of clean data, you can run it through a machine learning algorithm. I'm just going to do logistic linear regression and run them off. Okay. And then we can safely use that model to predict random test data, which has already been treated. And then here I'm just showing a plot on the x-axis is the predictions that we made with the model on the test data, and the y-axis is the true values. And you can see that we've got a reasonably good fit, which is what we want. So that's kind of an overview of how this system works. Now the thing is, this was synthetic data, and we want to know, does it work well on real data? And so one of the other things we'll do, and I'm not going to go over it because it's going to take a little too long to go over it, is we can run this data, we can run vtree on a dirtier data set. We can run it on KDD 2009. And I'm not going to, like I said, I'm not going to show you the whole run because it's going to take a little long. But just kind of show you what the data looks like. The data is about 45,000 rows, and what's noticeable about it is that it has a lot of missing values in it. In all of the rows, in all of the columns. And it has a lot of categoricals, some of which are very, very large. And if you actually try to just sort of naively run even a simple machine learning algorithm using this data, it turns out to be a little bit messy. I mean, this is how you might try to clean the data by hand, basically. You're going to try to get rid of all the ODAs. You're going to try to rationalize all of the levels so that you can see them both in the training and the test, and run the whole thing. And if you were to try that, you'll notice, if you go through this later, that even having done all of the training, all of the data cleaning by hand, that it's still hard to predict new data with the model because you're still going to run into the novel level problem and it's going to crash. So it turns out that you can actually do this much more easily. With vtree. So instead of having all of that hand data cleaning, you can just treat it the way that I showed. And what will happen is you'll actually get fewer variables than you would have had with the naive method. And you can actually run machine learning algorithms on it safely and evaluate them. So basically, you can run GBM on the data. And you can run GLM. And you actually get pretty good models.
So just to interject, the jump in model quality from naive to vtree, even after you get rid of the crashers, is about the same of the people that won the contest. The jump of AUC score was fairly significant. We didn't win, because they worked on it a lot harder, but the jump is of that scale. The naive treatment is not as good as vtree, takes 30 lines of code instead of 2.
And so that's, okay.
When you pick your calibration data, do you have to be careful about sampling? Like, for example, you have to make sure that the representation of all your predictor variables in your calibration set is approximately distributed the same way as it is in your training and your...
Yeah, you do. Yes, you do. Because basically, you want the data that you use to build the treatment plan to be representative of the data that you're going to apply the models to, and also the data that you're going to train the model on. So, yes, you want it to be representative, a representative sample of the data.
Do do you show in your code how you do that calibration sampling?
Yeah, in this situation, since we're generating the data synthetically, in the garden path section, I just generated another set. In the KDD set, we basically just randomly selected a subset of the data to be the calibration set. And the assumption is that with a random selection from the training set, it's going to have the same distribution as the training set.
But you could get unlucky.
You can
for
get
certain
unlucky, yes.
variables.
And I mean, that's an issue. That's why you have to be careful with, very rare levels. And that's why we want to evaluate what the significance of some of these things that we're pulling out are. Because if we got unlucky and we didn't get very much information, then we don't know very much. And that's just the nature of it. Okay? So those are some of the, go ahead.
Actually, I have a question. The first, regarding the slide you showed the zip code and the average, the difference between the average and each zip code.
Mm-hmm.
And you replaced this column instead of the zip code, so to compact the
Yes,
number.
yes.
Isn't it useful also to include the values, the Y, within each zip code? Instead of
You
using
can, that is one approach, but that is we get around that by actually, in our package, evaluating the significance of those estimates. We look at all of the individual levels. In addition to building the impact coding, we look at all the individual levels and we look at the significance of those variables, at those levels alone as predictors. And if they're, basically if they're not significant, then that's equivalent to variance being too wide, and then we can do the appropriate proof.
Second question regarding the way the package tunes the imputing. Is it always the statistical mean or median, or we can just configure it to k-nearest neighbors or some other imputing methods?
I'm sorry, repeat the question?
I mean, is the package, does it allow us to tune the way you compute missing values? Is it only the mean, median, or we can just configure it to k-nearest neighbor or
With our package, it is hard-coded to mean.
mean?
If you wanted to do something like that, you could. There's certainly no reason why you couldn't do an implementation that used a more appropriate substitution, but we just use mean because that suits the data that we happen to have. And so those are some of the operational issues that you can have in treating data. Just sort of in conclusion of this first part one, I just want to say that it's no substitute. Automated data cleaning is no substitute for getting your hands on the data. But some of these treatments are reusable over a vast number of domains and a vast number of data sets. So we encourage you to automate them so that you can spend more time working on more domain-specific data treatments that can't necessarily be automated, at least not at a large scale. And we have our own particular set of go-to data treatments, which suit the data that we use, may not suit the data that you use, and we have our implementation for them, which is featured. We have in the slide deck, we have some further references on some of the things that we talked about: the impact coding, the issue of hashing versus impact coding, and some of the statistical significance and goodness of fit estimates that we use to estimate the significance of variables. The V-tree package is on-prem, and there's also a slightly more beta version on GitHub. Again, we encourage you to take a look at it and either use it if it suits you, or borrow from it if it gives you inspiration for data treatment procedures of your own. And I'm just going to give you a little sort of pre-treat of what the second section of this talk is going to be about. We talked more about sort of the operational issues, but there's a couple of other issues that I haven't talked about yet that we'll get into more in the second section. And one is overfit from too many variables. Variable selection. Some people don't think about variable selection as being part of data treatment, but we're going to argue that it actually is, and John's going to give you some motivation as to why. And the other thing is false fit, and this, I have to confess, is sort of a problem that we kind of introduced ourselves by introducing the impact coding. The problem with the impact coding, the potential problem with the impact coding, is that you're using your training data to build these impact code models. And then you're potentially using that same training data to train your model, your larger model. This will cause can potentially cause upward bias in your performance estimates of the model, because you're kind of cheating. You're double dipping the data, and you're not actually training on data that's exchangeable with holdout data from the greater population. So we're going to talk about that issue, and I sort of touched on what you can do to mitigate it. Basically, you have a separate calibration set that you use to prepare the treatment plan that you do not use to train the model. And there are some other ways to do it too, which John will touch on very, very briefly. These are some new results, not from us, but from other people, on using data fuzzing and other differential privacy techniques to also try to mitigate this upward bias when you use nested models. And now, we can switch speakers.
Thank you. So I'm kind of excited because I actually got to steal the better slides out of Nina's deck when we were negotiating who does what. There we go. Okay, so I'm John Mount, the other author of Practical Data Science VAR, and the other consultant at Vector LLC. Nina basically introduced variable treatment for the very operational reason is you have to do it when you're using customer data. And KDD we bring out because our customers don't let us take their data and mock it at conferences. But KDD, she said there's only around 45,000 rows, and there was over 230 columns, most of which spent most of their time being nah or empty. And that data set really causes a lot of trouble. And the main motifs we noticed both in it and in customer data is, we're all operational. Like there's missing values that people put in nah or nan or infinity where we expected a number. Or this one has killed us again and again. We built a beautiful model on a categorical variable, and Wyoming shows up, and it wasn't in the training set. And we're not trying to make a good prediction for Wyoming. We're just trying to prevent the system from crashing in a statistically valid way. And the last one, which is the one that actually fascinated us the most, was categorical variables with very many levels, like zip code. And again, we're in the age of big data. You may say 40,000 possible levels isn't very many, but when your client only gives you a couple 100,000 training rows, you don't have enough data to statistically learn the interactions of those zip codes against every other variable. And that's why we suggested effects coding, is the name we used back from the 70s, that, look, let's just try to find the effect of that variable, and let's give up on trying to model interactions. We don't have enough data to support that. And the problem is that really attractive effects coding hides a statistical problem that I'm going to talk about a bit here. What we're worried about is that we might build treated data that looks really great. That the machine, what we're doing when we impact code something like zip code with 40,000 levels, we're taking a variable that, yes, R, when it processes it, is going to splat it out to 40,000 dummy or indicator columns. It has 40,000 degrees of freedom in there. It consumes 40,000 data row degrees of freedom in the model. We correctly recode that for a linear model. We've hidden that degrees of freedom from that model. It gets this psychic variable that it says, there's no way I'd do this good with one variable. I'm a genius. And it's like, well, it's not one variable, it's 40,000. This leads to overfitting in training. And why we care? Right, so Nina touched on a very important point. Is variable selection part of data treatment? I mean, we have very good machine learning algorithms now. Why can't we leave it to them? And the answer is, most of the common best-of-breed machine learning algorithms don't understand wide data to this age. And again, you may think that 230 columns isn't wide data, but each categorical variable is hiding more variables in it. And we can basically, in addition to the fact that modern machine learning doesn't actually work very well on wide data, which I'll demonstrate, we've also copped to, and I noticed other people perking up when Nina mentioned it, that we're introducing a modeling bias by doing this effect or impact coding. And we need to get around that. I just read through that slide. Okay, so here's the demonstration that for at least the following machine learning algorithms, and probably many more, but I got bored. Decision trees, logistic regression, elastic net regression, gradient boosting, naive Bayes, random forest, and support vector machine. I can build a data set that has no signal. I build y independent of x being the independent variables, y being the dependent variables. So there's no possible signal. I can get arbitrarily good fit on training. These guys, some of which claim to use cross-validation, some of which claim to use regularization, don't get the joke. That they, instead of saying there's no model, they work very hard to build a model even when there's no effect. Then this model fails on test. And this is the typical one. We get this from a lot of clients with more junior data analysts. And this is the receiver operating characteristic plot, ROC plot. And then basically, they run random forest, and random forest is my favorite algorithm for this, on their training data. And they've gotten area under the curve of 1, which means there's parameter settings for this scoring function that find all the positives while bringing up none of the negatives. Perfect prediction. How can you not like that? Well, what happens is we give them a holdout test, and they get AUC of 0.5. That they learned no model whatsoever. And this is weird, because if you read the random forest literature, it's regularizing by bagging. It has cross-validation built into it, some of its many, many details. But for one data set, you can defeat it. And there's a sort of folk theorem that they then hope for, going, okay, admit it, I'm not going to get AUC1 on real data. I know that. But if I have AUC1 on training, maybe I can get 0.7 on test. Maybe there's some theorem that I get to keep some fraction of my overfit. And the answer is no. That severe overfit is not evidence of model. And again, all statisticians know that, but all data scientists sort of hope the opposite. So we'll just work through this bad, I used to call it bad Bayes because I designed it first to defeat Bayesian algorithms, and then I was able to defeat every other one. And it's, sorry about this, my screen's a little smaller than I'm used to. Again, we give the URLs for the entire set with slides, so any link you see in the talk you can get to, and we give it again at the beginning and end of each talk. But all these demonstrations are markdown sheets, so you can run them yourself if you load the set of libraries we described, or you can just look at the pre-made HTML. But here's the bad models.html, which I guess is better than bad Bayes, because it's not really the model's fault. So what I did is I wrote a bunch of R code to generate synthetic data sets that nobody cares about. And then, but the property of the data sets is the y's are generated completely independently of the x's. And then when I'm speaking, x's are input or independent variables, and y is the quantity to be predicted. So I just generated them independently, so there should be no relation. Now, here is naive Bayes on its training data. And this is the receiver operating characteristic plot, and it says for every false positive rate on the x-axis, what true positive rate can I pull? And this curve being very large and shaded in is good. So this has an AUC of 0.86. That this is a pretty good model. That this model would make you money on your training data. Here it is on test. Here is a decision tree, doing well on training, failing on test. Here is, and again, you can run all this code. This is one of my favorites. This is a GLM. It thinks it's doing pretty well in training data, but it also got this diagnostic that fitted probabilities numerically 0 or 1 occurred, which is one of the many symptoms of that model had quasi-separation and was trying to run to infinity, so you should expect really perverse behavior. And it didn't do so well in test. Basically, remember on an ROC plot, having the plane half shaded in means you learned absolutely nothing. The random line, I call that actually the KDD plot, because I once saw somebody presenting this, that AUC 0.5, they've at least got half of 1, which is not so true. Random forest, dominant of the overfitters despite the bagging. How did I do that? So random forest is superior to bagged trees because it builds models by selecting subsets of the variables for calculation, which increases model diversity, and then building different tree models and averaging them together. So the way we defeat that is we duplicate variables, which is very common, because remember, what a statistician considers variable is basically a curated variable. What a data scientist considers variables are columns in database columns or joins. So it's often we'll have columns that imitate each other, because we don't curate, we join and head into the data science. So here it is on test. Support vector machines. Now, little philosophical thing that obviously support vector machines with a given complexity have a given guaranteed generalization error. But the problem is the support vector machine is willing to make very complex models, and we normally don't inspect did it make a complex model or not, and it did the same thing. And elastic net, I forget the exact parameters I used, but not so good. Gradient boosting, which is actually currently our favorite machine learning technique. It's basically been pretty good, not so great. So that's called bad models, previously called bad Bayes. And the argument there is that is why you need variable selection, that the types of data sets that us data scientists build by this willy-nilly joining of columns from many sources, they overwhelm all the best of breed algorithms. And usually it requires one more mistake, like duplicate columns, that something to cause its significance calculation to be wrong. So you need to defend these algorithms with an initial variable selection. And we've tried to design VTreat and our philosophy of variable treatment to do the variable treatment should do as least as possible. The machine learning algorithms are smarter than what Nina and I are going to write. So anything good we should leave to them. But anything that they can't survive, we need to do for them. And that's why operational issues are if they're going to die on non-number, take it out. If they can't take large categoricals, for instance, the random forest default implementation used to take only 32 levels. I think now it takes 63. GBM can only take categoricals with 1,000 levels, which is way less than 40,000. They literally crash on those. So we need to defend. Okay, so we've defended. Now, from this point on, everything's our fault because we messed with the data. So why are these models failing? It's basically what a statistician would call regression to the mean. That each variable, even without our V-treating, is essentially a one-variable model. And when the model is building up of a lot of variables, it's measuring variable performance at some point in some implicit way. Like when it's building trees, it's selecting them. And your top performers, once you have enough variables, tend to be there mostly by luck. And so like suppose each variable maybe has a 60% accuracy plus or minus 10. Well, then your 70% accurate variable might actually be a 50% accurate variable that got 20 points lucky, if you have enough variables, enough venue shopping to go from. So your machine learning algorithm changes variance, which is the uncertainty of measurement during training, into bias, because it picks people that empirically perform well. And so that's the problem, that you're basically converting variance, which is bad, to bias, which is worse, by training. And also Friedman wrote on this, that even the nature of selecting variables introduces bias, let alone conditioning them and changing them. So why don't bagging and regularization fix this? These are two of my favorite modern machine learning techniques. And so bagging is the averaging of many models to reduce variance. And that's the answer right there. Bagging doesn't help against bias. And regularization, if you trace the literature, is essentially assigning a prior to all models. So by the Bernstein-von Mises theorem, as I add more data, I overcome that useful regularization of keep the coefficients near zero. As I add more data, my data becomes more capable of running away from that initial regularization term, and then I overfit. So what to do? We're actually, yes?
Doesn't cross-validation help then?
Well, that's the thing. Is, so
It's weird, right?
all these things claim to have cross-validation baked in. And what we did in the graph I showed you was cross-validation. And all it showed you is your modeling technique failed you.
And you used k-fold, 10-fold cross-validation, or?
I left them at defaults. So if you upped them, none of them could defend themselves and improve. But then I would just have to build a more vicious example.
Sure.
But yeah, the cross-validation is the gold standard. It's the only way I'm even noticing the effect. And so if a machine learning algorithm has strong enough cross-validation, it can probably defend itself. And we're essentially introducing cross-validation throughout. But what will not save you are statistical adjustments or priors, that you basically need to look at fresh data. So what we do is we just bring back the classic statistical idea. Let's just sort by significance. And what we're going to do, and this is kind of a cute idea Nina came up with, what significance level? In VTreat, we deliberately put no default on the significance variable. Like we put defaults on tons of variables, but not on that one, because we don't want it to be our fault what significance you pick, and we're not going to type in 0.05 for you.
But the point Nina had is, suppose we put a significance of 1 over number of variables. Like the KDT had about 250 variables. So what if we put significance 1 over 250? And suppose all 250 variables are gibberish. Well then, about 1 in 250 of them should sneak through the filter, which is about 1 over 250 times 250, about 1 should. So a reasonable number of crummy variables will sneak through our significance testing, but it's a small enough number that the downstream machine learning algorithm can now defend itself. So we're just saying, we're not trying to eliminate all the bad variables, we're just trying to cut them down to a reasonable number such that downstream machine learning, which is often quite brilliant, can cope. So why aware reduction? This is the sort of the weird bit about V-tree, is the effects encoding variables are encoding based on Y, knowledge of Y during training. And this is why we get into some problems with significance, which I'll get into. But it's a great thing to do. And it's, so here, this is again included in your demo set, and it's the preparing data, bad models, Y-aware reduction. And we're not running V-treat here, we're just writing some toy code that's small enough we can type in directly, which we share with you on GitHub. But we're building another bad Bayes type model, but this time there's a few signaling variables that were involved, are correlated with Y, therefore should be useful to help predict Y. And there's a bunch of pure noise variables that have nothing to do with Y. And the idea is, with enough of these noise variables, they cut in front of the signalers. They get lucky during training, get the award, and then do nothing during test. And the way you see this is, here's a GLM trained on this data unprepared. So there's no NOS. This is clean data. It's just horrid data. And it gets this perfect score on training and this middling score on test. And also this ROC plot, all the dots are kind of concentrated, and that's kind of weird too. It means that the score of the classifier is probably highly concentrated at one value. So the score of the predictor is concentrated at one value, so you can't really make different classifiers out of it. You only have one threshold. Typical for naive Bayes, but not GLM. So then we can do, let's defend ourselves by principal components analysis, right? If we were sociologists, we would never put data into a generalized linear model without principal components analysis. And this is what I hate. Principal components analysis is an X alone preparation. So the noise variables they vary in different ways, so they get to contribute principal components. And then all the signaling variables are correlated with Y, and therefore correlated with each other. So actually, they don't get as many principal components. They're actually at a disadvantage because they're actually useful. And so on training, we now only do 0.77 AUC, but on test, we do an even worse 0.58 AUC. And it's because the noise variables not only got ahead of the signaling variables by chance, but they actually have an advantage because they tend to be more orthogonal since they're completely unrelated to each other. And this is why I'm on record as hating principal components analysis. I would suggest things like partial least squares, which are at least somewhat more Y-aware. That you don't want to explain all the variation of your input variables. You want to explain the variation of them that's correlated with what you're trying to predict. So here's the same GLM with basically all we did is Y significance testing. So we took each variable and we said if you're insignificant, you don't get to go to the GLM. So we built a one variable model just on that variable, check the significance of that model. If it's not great, you're out. And obviously this is not coordinate free. We're testing per variable. But again, in our mind, variables aren't dimensions in space, they're database columns. The frame of the database column is a special set of coordinates. And so this fits the AUC 0.79 on train and a 0.8 on test. It worked. And this, GLMNet, it turns out GLMNet with the proper L1 regularization turned on can do the selection all by itself. That's pretty awesome. And this, that's why all these L1 regularized machine learning algorithms are kind of cool, that they bake variable selection in because they tend to like to turn variables off. However, we can overwhelm them if we give them too many. And again, we're not here to sell retreat. We're here to sell the idea of automating what you can so you have more time both as the data science practitioner and the downstream machine learning algorithm to do something good. So are we done? Well, let's remember this line that Nina hinted at. We can accidentally introduce one issue ourselves when treating variables. The impact coding itself is not safe. Now, obviously, people have asked, you're using the mean, that's not very intelligent. We'll grant you that. So the impact variable may fail to capture a lot of information, and you could basically encode more. But the other thing is you're also maybe encoding too much. The impact variable itself is hiding a lot of degree of freedom and possibly memorizing the training data in a non-productive way. So the idea is, remember I said that think of variables as single variable models. Well, therefore we have a nested model. That we're building a model not off original data, but off modeled data. And nested models require some additional care. So these are the diagrams that Nina worked really hard on, and I got to use them. But so here's what we tell all the undergrads not to do. Don't take all your training data, run it through your training, use it all for training in your algorithm, build a model, and score on that same training data. We don't do that, right? Because we know that for many machine learning algorithms, they tend to do well on their training data. There's an upward bias, they've seen that data. So we tell them, do this. Do a test train split, use some dominant fraction of your training data for training, and a disjoint fraction for test, and score on the test. And that's the graphs I've shown you, and they show when overfit occurred. The problem is, once we introduce variable treatment, this procedure is no longer strong enough to defend you. We're doing cross-validation, but we need even more. We need this diagram, which looks really complicated, but it's only a single line of code. Split your training data into 3 pieces. And tips running hasty do things like this too, is reserve some bit for calibration. That bit goes into vtreat and is never seen again. We build a treatment plan off it. The training data is run through the treatment plan, then given to the machine learning algorithm to build a model. The test data is also run through the treatment plan, and then scored. So we basically have a 3-way split. And that gives us a reliable estimate of model quality. So, so the reason is that these high-level categoricals, like Nina did a demonstration of a categorical that had 200 possible levels on a 500-row calibration set, or data set. So each one of those levels is only clearing about 2.5 times on average. They're memorizing their Ys. That we don't have a good estimate of what the true relation between these levels and the Ys are. We just have a good memorization of the training set, which then a linear model over that will say, yeah, Y equals 1 times this treated column. That is my perfect model. And that is wrong, because that doesn't work in test. So I'll run the nested example, and this is where we're going to get into differential privacy, which is kind of a cool idea. Not ours, but still kind of darn clever. There we go, sorry about that. Again, so we're supplying you this code. And this one I want to look at, we have text in here, so it works good even without us. But, so here's a Bayes model, and what we've done is we're building a data set with large categoricals, and then we're running a vtreat-like procedure on it, just some hand code we typed in, that we're re-encoding this large categorical with hundreds of levels into an impact, that I tend to contribute to Y, or I tend to go against Y. And the problem is, we build a model on that, we get perfect performance on training, which I'm showing with this graph, and horrid performance on test. And we can also use a technique of Misha Belenko, who I think is Microsoft research, called learning from counts. And instead of encoding it as a Bayesian submodel, he records 3 or 4 numbers that the Bayesian model is in the linear span of, like the numerator, the denominator, and some other stuff. And he's noticed the same effect, and he spoke on this at the recent data science conference, a Dato conference a couple months ago. And he saw the same thing, gets perfect performance on training and perfectly wretched performance on test. And it's an overfit technique that the re-encoding is hiding. He called this learning by counts. Well, one way to get around this, and again, I tend to prefer standard statistical techniques. They've been discovered before, they work well. Jackknife it. So what we do in this theoretical one, not in vtreat, is we build this encoding, but we build it many times. So if we're going to encode this row, we use all the other training data to build the encoding, and then we encode the row, and then we throw the encoder away. And then for the next row, we use all the data disjoint permit to build an encoding. So now we've got a data set for training where every row has been coded, but never been involved in the design of the encoding it's in. And obviously for a Bayesian technique, that's very fast. You can do that in constant time. And the jackknife model works. That you see the AUC on train is this beautiful 0.94, a very predictive model, and on test it's 0.93. And it's because, as Nina said, because the training data was prepared using conditioners that it was never involved in the construction of, it remains exchangeable with future test data. That's what happens about future test data. Future test data wasn't in your treatment design, but your training data was. That's why they become inseparable and your performance changes. So if we jackknife the preparation, we maintain that exchangeability with the future, and the model works wonderfully. And same for count coding. Misha actually hates this method, but tough. I think it's the best. The other technique we said was split model. So basically, reserve a fraction of your training data for the building of the encoding and another disjoint fraction for building models. Now remember, we're in the age of big data, and that means we all write these essays about how hard it is to run through databases. But the cool thing about big data is you can waste data. So using some constant fraction of it for calibration, that's fine. And so I think we have to think more about wasting data. And that does the exact same thing. It gets great performance on training and good performance on test. And then vtreat itself has an experimental cross-jackknife attempt where it uses all the data to build the encoding, so you get the highest quality, lowest variance encoding. Because again, the more data you have, the lower variance you get. And then it builds a jackknife training set where it's basically not used that encoding to prepare the training set. So you use that set for training and throw it away. And that gets really good performance also. 0.95, actually, that's on training, that's a lie. 0.92, so it's dominant, it's in there. And then Misha Vilenko introduced a really clever application of differential privacy, which we think is not getting enough attention. It's not the same one as in the science paper of Dwork et al. But what he noticed was the differential privacy was invented to do analysis over sensitive data to try to make it difficult to find an individual in a database, like de-anonymizing Netflix. Differential privacy is invented to try to prevent that. Well, the idea was that if you don't know what data you analyzed, how are you biased? So what he noticed was that if you built your encoding strategy, and he calls his coding by counts, using differential privacy techniques. So you never actually look at the data. You look at an oracle that gives you differentially privately safe answers about the data. Then you can't memorize the training data because you never saw it. And it turns out, this is all big words, how do you usually establish differential privacy? It's usually by adding a little Laplace count noise. So what he noticed is, in learning by counts, if you just noise up the numerator and noise up the denominator a little, you get good training performance and good test performance. And he's actually able to use this in an online algorithm that he can take incremental data and go. And the idea is, any common categorical that occurred 10,000 times, you add 5 to the numerator and 3 to the denominator, no change. Any rare categorical that only occurred 2 times, you add a little bit of noise to the numerator, a little bit of noise to the denominator, you nuked it. And that led us to look at, well, what's that about rare levels? That's what rare levels are doing. They're overfitting and encoding the training data in a non-useful way. So we added to vtreat the ability to prune levels out of the cat-n variable. So basically, rare levels, and they're also eligible for pooling, as Nina said, but rare levels don't code. And it turns out we were able to get similar performance just by adding that to vtreat. Though the differential privacy technique is kind of cute, and we have some writing on that. So that's the danger of nested models, that basically you drive overfit by overfitting the training data and hiding the number of degrees of freedom from the downstream modelers. They think they have a single variable when it's actually a variable that had 40,000 levels and successfully memorized the training data. So why does significance pruning work? I kind of have one issue with how stat is taught. It's usually taught procedurally. Do this because we know it works and it's none of your concern. And obviously significance pruning is a very good idea, but what's motivating it? And our suggestion is it's imitating a permutation test. And that's how to think about it. And the permutation test itself is fairly expensive to implement, so we use significance testing. But the idea is, what does an X that's not correlated with Y look like? And one of the properties it has is if you permute the Y's, the relationship's about the same. That if X and Y are independent, and I move the Y's around, like see in the first row I now have Y4 instead of Y1. Well, they weren't related before, they weren't related also after, it should be about the same relation. If they were correlated, I've now just broken the data. And the idea is that we can do that permutation test, that we run our magic modeling procedure, whatever it is, be it the V-treat prep step or GBM or something expensive, and we run it on permuted data again and again and again. This gives us the distribution, which is the black hump, of what nonsense fits look like. And here we're scoring by deviance, so low is good. And if our actual model, the unpermuted data is way here on the left, and the distribution of all the crummy models is way here on the right, then we have the usual sort of thing, we're plausibly not one of the crummy models. Whereas if our fit is typical of the permuted sets, we have no evidence we've actually fit, no matter how far we've reduced the deviance. We just have evidence that we have nothing. And so to test a variable for signal, we would say the ideal Gedanken experiment is build a one variable model, so predict y using only a single variable, and then do it again and again for permuted versions of the y. If your model is out of that pack, you're probably good. If that model is in that pack, you're probably bad, or at least you're indistinguishable from noise. And we say you're a good candidate to prune. And then the punchline is that's essentially what significance testing is abstracting. But we're not endorsing the whole frequentist framework. And so there's a lot of assumptions here, most of which are going to be false for different data sets. The variable signal will manifest itself through a simple linear or Bayes model. So we're not using very complicated models for these one variable models. I might want to use something like a generalized additive model, but it's more expensive. I'm doing this to a lot of variables. And it's sort of the idea if the variable's complete, I mean, there's definitely situations where the correlation's not obvious till a second variable enters as an interaction, but in real data, we usually find out that the variables get less predictive as your models get better, empirically. I mean, obviously that's not mathematically the case, but the idea is that you're lucky if a variable that explains 10% of the variance alone still explains 10% of the variance when it's in a larger ANOVA table. So we're going to just take their single variable performance as a stand-in for how good they are. Then we're also not considering whether variables are duplicates of each other or interactions or anything else. We're leaving that for the downstream machine learning algorithm, except for the cat variables. Since they're encoded, they've lost any ability to do interactions among levels. Bummer. So wrap up a little early. I'm sorry about that. So the conclusions are you have to prepare data prior to analysis. And that's not for statistical reasons, it's for operational reasons. That you're going to have NAS, you're going to have invalid values, you're going to discover new levels during application. Like you're going to deploy a machine learning algorithm into production, Wyoming shows up and crashes the whole stack. And you're going to encounter variables that have an extreme number of levels that you want to use, not just throw out, like zip code. And you won't always have the domain knowledge to do a successful join. Or you could do that plus this. So we need to automate those steps so we're not wasting a lot of time on it. Nina's demo of KDD naive, it took us hours to write that code just to get the thing to not crash. And even then, it was horrible. So with V-treat, it's a one-liner because we spent those hours reusably. And again, we're not pushing the library, just take the techniques and add them to your own quiver. So even though the reasons you were processing data were operational, you soon introduced statistical flaws. First, you have a certain insensitivity that any of the cat variables you've introduced are only using simple means, so might be vulnerable to outliers. And so you're not encoding a lot, but you're also encoding too much. Because the cat variables had a lot of levels, they may have memorized training data in a non-productive way. And there are a lot of good techniques to efficiently correct for this. And basically, we found that merely significance pruning on levels, not on variables, but on the levels hidden in the variable works. We found that reserving a calibration set works. And again, in the era of big data, we shouldn't be embarrassed to waste a little data that way. And we've also found through other sources that differential privacy works, that it can decouple models and say you can train nested models successfully. So further reading, VTreat, we're developing more and more vignettes to try to explain the technique. For model testing procedures, we wrote a series we're quite proud of. Again, these links are all in the slides which we're sharing. We wrote a series on comparing all kinds of model testing procedures, like how does cross-validation differ from significance testing, differ from permutation testing? And it turns out they're all testing different things. Nina's got some neat work on permutation tests, and we also recently wrapped up a series on differential privacy where we cover both the Dwarf paper, which basically made stepwise regression safe. Made stepwise regression safer, and also the counts effects where you make nested models safer. And basically all the materials are available here on GitHub, including these slides in the subdirectory. And VTreat has been in production on CRAN for a couple months, so we're trying to stabilize it and not add improvements as often. And it's definitely the first thing we try for our clients. And again,
it seems like the methods that you mentioned, if you have a bunch of collinear variables, it seems like if one of them makes it through, they're all going to make it through.
yes.
So how do you deal with that?
Well, let me repeat that back just in case. So he said basically if I have a bunch of collinear variables, if one of them makes it through my selector, all of them make it through. And that is correct, because I'm not doing any sort of deduplication. And I hinted at that with the bad models, that duplicate variables seem to defeat random forests thing. And the reason is that it is trying to get variable sampling to cause model diversity. That what random forest needs is model diversity, and it's hoping that sampling establishes diversity. And it does until you have duplication. So the honest answer is one of these bad models could slip right through VTreat and break random forest. So we don't do anything to do that. So we would suggest possibly a principal components analysis, or even better, a partial least squares, because that's why we're right after the VTreat. And so that way you've limited variables down to those that are somewhat correlated with Y, and then you're trying to get an approximation of the simultaneous variation right after.
Or you use a machine learning algorithm that's robust to collinear variables.
Nina had a good point. She said, or use a machine learning algorithm with robust to it, and I think decision trees is the candidate there, because they don't, decision trees, each variable is used after others are applied, so it might be immune to duplication. It may just consider them two opportunities for the same variable. It's an interesting question.
Without too many linear models are also somewhat robust.
Regularized linear models. So yes, that's the other one. Is Nina's done a lot of the math on this, so I'm sort of stealing her answer. So she's also saying that regularized linear models, in this case L2 regularization, not L1. If you had a bunch of collinear variables, they smear the coefficient all across all of them, which is a fairly safe thing to do. So GLMNet has a nice family of generalized linear models, so they do well with variable duplication. Yes?
How's the VTreat, did you try it in programs like fraud detection where you have unbalanced Y?
Whoosh, I couldn't hear you. Just kidding. So the question is, have we tried VTreat in cases where there's unbalanced classes like fraud detection? And the answer is no. Most of the applications we've done have been fairly balanced, where maybe the target class is about 10% of the data. And as you obviously are hinting at, VTreat's using bulk mean statistics to drive everything, so it's going to have problems with that. It does accept a weight parameter, so you could try to force it to consider the two classes as balanced, but we've not done that. And he's very correct in pointing out that if the target class is rare, it's a lot harder to trick out these statistical things with a bit more care than we've done. Otherwise, I didn't hear the question. Yes?
I got two questions. So you showed a bunch of models that actually worked out really well for the regression.
Yes.
How do you choose the best one out of all those that worked? Just based off of the highest area of the curve? Or?
Wow. Okay, I'll let you have your other question also. Go ahead and do this one first. So I showed a bunch of models, some linear, some nonlinear. How do you pick the best one? And did I use area under the curve as the criteria? Honestly, we used area under the curve because that was the criteria for the KDD contest. I don't like area under the curve, to be honest. It has one nice invariant that it doesn't care where you pick your threshold, that you're immune to any monotone transformations. That's nice. We usually use deviance because that's, get the model right. I don't care whether an adjustment of you is right. I want you to be right. Then how do we pick? Honestly, not systematically. We usually start with our favorites. GLM first. If nobody does much better, we stick with it because it's simplicity. And then we'll try GBM, and then basically only move on with forced, or if we know something about the problem structure. Like for instance, trees are invariant to any single variable input transformation or any single monotone input transformation. And so we try to think, what are the properties of the problem for that? We don't have, once you've looked at more than one model, I don't have a principled way of saying which one's best. And you have another question?
Yeah. So when you do variable selection, why not just do stepwise regression? Why go through all the other?
Ooh, well, okay, so why not just, again, I'll repeat the question. So why not do stepwise regression instead of variable selection? Well, I mean, it's a good idea. So it's not efficient for many algorithms. For instance, R, the default stepwise regression requires building the full model. So that usually will crash. So obviously a more intelligent stepwise regression wouldn't have this flaw that R has. And then the other problem, and it comes up in the Dwork science paper, is as you get into the stepwise regression, you get an overfit problem that your performance on training, incremental performance on training data is not representative of incremental performance on test data. And
I just wanted to
okay, cool. And the reason is that you're looking at a lot of models when you stepwise regress. However, we like stepwise regression when you can do it. And sorry.
We like stepwise regression, but it's not always safe, especially if you have a lot of variables that you're combing through. Because one of the results from differential privacy is that there is a limited number of times you can go back to the well. Every time you look at your training set again, you're biasing it. So if you go back too many times, at some point you can't start, it's not safe anymore. And so it's not a bad idea to actually prune by an alternative method first, and then once you have a sort of reasonably small set.
Yeah, and it's a really, we lost the screen, but I've tried to plug it back in a couple times. And also, I come from a computer science point of view, and back then I was like, let's learn the XOR problem, that more variables are better. Now that I've been in industry for years, I have this more pessimistic that each variable is never going to do better than it does alone. And that's obviously not true empirically, but the idea is that the initial step in stepwise regression is probably your best guess of the variable values. But you could cut to, it's a great topic, and I definitely suggest reading, especially our write-up on the science paper, because stepwise regression is very tempting, and it's obviously a standard practice. There's some issues. Did anyone else? Are we good? I'm really sorry we lost the video, but the URL's shared. Your fault? That's more interesting than I said. Anyway, to be honest, variable prep is something we're very excited about. We don't think it's one size fits all. We've supplied a library for the least common denominator, which turned out to be fairly complicated to develop because even the least common denominator took a lot of work to get right. And we say that the analyst shouldn't be dependent on it, but it should free up the analyst to do more intelligent things, like variable conversion, joining to domain knowledge. And thank you very much for your time.